muchas gracias a todos por venir a esta charla, a esta nueva charla del ciclo Hablemos de Física. Y nada, brevemente pues quisiera agradecer a Sandro Stringari, profesor e investigador en la Universidad de Trento, en Italia, que nos acompaña hoy, y muchas gracias, Sandro, por tener la oportunidad de escucharte hoy y hablarnos sobre pues, la condensación de Bose-Einstein y la superfluidez en gases atómicos ultrafríos. Le voy a dar la palabra a Fernando Sols para que bueno, pues, introduzca un poquito y os hable sobre el conferenciante de hoy. Muchas gracias.
Pues nada. Bueno, en primer lugar, muchas gracias a África, a la vicedecana África Castillo y a la decano Ángel Gómez y en fin, al equipo decano en general por su flexibilidad para organizar este coloquio hoy en un día y una hora que no es habitual, pero era la única posibilidad porque mañana participa en un workshop que tiene lugar aquí jueves y viernes. Entonces, pues como Sandro es italiano, le presento en español y él ya entiende lo que estoy diciendo.
Okay.
Entonces, bueno, es un placer tener aquí al profesor Sandro Stringari de la Universidad de Trento. Él es una figura muy, muy destacada en el mundo de la teoría de gases cuánticos y de sistemas de muchos cuerpos, de many body. Él estudió en la Escuela Normale Superiore de Pisa, después hizo estancias en Oxford, y unas cuantas en París, que suman hasta unos 3 años, tanto en Orsay como en la École Normale. ¿Se me oye bien? Y su tesis, bueno, el equivalente a su tesis, porque en aquella época en Italia no hacían tesis, pero empezó trabajando en física nuclear y a raíz de un encuentro con Lev Pitaevsky, pues empezó a trabajar en líquidos cuánticos, sobre todo en helio 4, superfluido, en clústeres de gotas de helio 4 y entonces entonces cuando llegó el tema llegó la realización experimental de la condensación de Bose-Einstein, pues él ya llevaba un tiempo trabajando en gases cuánticos diluidos y entonces hizo trabajos muy importantes y organizó reuniones muy importantes. Hubo una muy importante en Italia en el año 93, de la que salió un libro conocido como Libro Verde, en que los editores son él junto con Dave Snook y con Alan Griffith, y que se publicó en el 95, justo unos meses antes de que se realizaran experimentalmente los condensados de Bose-Einstein en gases cuánticos diluidos. Y eso fue muy útil porque había un conocimiento de teoría bastante extenso que permitió progresar muy rápido en el campo, también por el trabajo que históricamente habían hecho en los 60 gente como el mismo Lev Pitaevsky. En fin, él es una figura de referencia, jugó un papel de liderazgo. Él organizó la primera escuela sobre el tema en Varena, una escuela de la serie de Enrico Fermi, estas legendarias escuelas en el lago Como, junto al lago Como, que en fin, por las que se ha paseado multitud de grandes físicos. Entonces, a partir de esa época ya él empieza a concentrarse en los nuevos gases cuánticos y ha trabajado en muchas cuestiones de los gases cuánticos. Ha sido y es una de las figuras teóricas más importantes. En particular, dentro de su labor de liderazgo, cabe destacar que ha organizado numerosos workshops y escuelas de verano. Ya he mencionado una, pero es que luego ha organizado varias más. Y todas estas son reuniones que han tenido una importancia muy grande, han sido de referencia. Quizá una cosa también que cabe destacar es que en Trento creó el BC Center, el centro de Bose-Einstein Condensation, de BEC, que ahora hace un poco lo han denominado, han pasado a denominar el centro Pitaevsky BC Center, porque Pitaevsky, con el que ha tenido una gran asociación, se murió hace unos meses. Esto es algo también importante de destacar. O sea, Lev Pitaevsky en el año 89 empezó a visitar Trento y ha tenido una relación muy larga y muy duradera, profesional y muy fructífera con Sandro y su grupo, y en particular desde el año 98 pues ha sido profesor en Trento. Entonces Lev Pitaevsky, que es una figura legendaria de la física rusa, es uno de los coautores de Landau en la famosa colección de física teórica, pues ha tenido una colaboración muy estrecha, han escrito muchas cosas juntos y Sandro Stringari ha hecho una gran labor en traerle al mundo occidental y que digamos, es que haya podido estar cerca de todos. Finalmente quiero destacar que entre las muchas cosas que ha publicado, en particular hay un review sobre Físicas del año 99, que fue el primer review largo que se hizo sobre el tema, que tiene ya más de 4.000 citas, es el artículo más citado en el campo. En fin, todo esto da una idea. Dentro de gases cuánticos debo decir que ha tocado prácticamente todos los temas posibles, interacciones spin-órbita, supersolidez, en fin, you name it, ¿no? O sea, y hoy nos va a hablar un poco de un resumen de la historia del campo en los últimos 25 años, digamos, y seguro que sea muy interesante. Bueno, pues con esto ya paso la palabra a... The floor is yours, Sandro. Thank you very much for coming. Okay.
Okay. Thank you very much, Fernando, for this introduction, this beautiful introduction, and for inviting me to visit your faculty. By the way, this is my first visit to Madrid, and I always like to organize such a visit, and this was a wonderful opportunity. So I have organized my talk in a way just to give a flavor of what is this field of ultra-cold atomic gases, where are we going now, and so it will not be very technical, and I hope that this flavor can stimulate interest in the field from people also who are not working directly on Bose-Einstein condensation. And I would like to start my presentation by discussing about temperature. In this slide we have a logarithmic scale of temperatures. So each steps, if you go up, increases the temperature by a factor of 10. And you can see that using this scale, all the temperatures are a little bit compressed. And for example, the temperature where we live, that is in between the boiling water and the freezing water temperatures, between 0 and 100 Celsius degree, is very, very close each other. And for example, even the sun surface has a temperature which is not so far from this temperature if you use this scale. And this just to give you how far we have gone in our field down in temperature with respect to the room temperature. And we have a very famous temperature scale with liquid nitrogen and a temperature of the order of 1 Kelvin degrees, where we have the standard regimes of superfluids and superconductors in physics, but we have also an important temperature characterizing the temperature of the cosmic radiations. But then if you go down, you have to work a lot. You can imagine how experimentalists were able to work to reach down this temperature. And this is the regime of quantum degeneracy in dilute ultra-cold atomic gases, where I will present most of my results. But I would like also to give a look at what happens if you go to higher temperature, in the opposite direction. And in particular, if you go very, very high on the scale, you reach a very, very high temperature, and this is the highest temperature that have been realized in a lab in Geneva, the collider in Geneva. And where one can reach this temperature by colliding protons and antiprotons. And this temperature, in connection with the usual theory of the Big Bang, is a temperature which does not correspond to the beginning, where temperature is in principle infinite, but not so far. And so In this experiment, one explored this extreme condition of metals, which are of high interest for high-energy physics. What about the lowest temperature? The lowest temperature achieved in the lab was done, maybe this is not the record, but not far from it, 10 to the minus 10 Kelvin degrees. And this was obtained by in the group of Wolfgang Ketterle, that I understood he was visiting your faculty some time ago. And I would like to show this picture because it gives a feeling of what type of labs you need to work with to reach these temperatures. But the question that I would like to address now is why do we need to reach such low temperatures? And the reason is that we want to reach a regime where quantum physics becomes important and where the atoms do not behave like classical particles, but behave like waves, like according to de Broglie prescription. And an estimate of the de Broglie wavelength can be given in terms of temperature for a classical gas using this well-known formula. And here I give you two examples of what the value of this lambda wavelength at room temperatures and at the temperatures which are relevant for our experiments. And what's important in order to observe quantum effects is that this length, the de Broglie thermal wavelength, should be larger than the interparticle distance. And this is the reason why you need to go to very low temperature. And the problem is difficult also because if you want to work with a gas, as we want, you should work with a very, very dilute gas, much more dilute than the gas that we use at room temperatures. And so the interparticle distance is very large for these gases. And so you have to go to beat this length, go down to temperature, which are this record temperature of 10 minus 8 or 10 minus 10 Kelvin degrees. And in particular, when you decrease the temperature, the thermal wavelength becomes larger and larger, and eventually comparable or even larger than the interparticle distance. In this regime, as I was saying, atoms behave like waves, and they lose their identity, and they behave, they can give rise to new phenomena that are the topics that we want to discuss. From this point of view, it's important to distinguish the fermions between bosons, which are different particles that nature exhibits, and according to which fermions are electrons, neutrons, and other photons, protons, atoms with the odd number of fermions. And while bosons are photons, atoms with even number of fermions, and helium-4 is a typical example, but also the atoms that we use now to realize Bose-Einstein condensation belong to this category. And the new phenomenon that takes place at very low temperature is known as Bose-Einstein condensation. And this is illustrated in a very nice picture here that is due to Wolfgang Ketterle, where you see that when you are at high temperature, the atoms behave like billiard balls and so classical objects. But when you lower the temperature, at some point the wavelength, the de Broglie wavelength becomes comparable to the distance. And when you go down, 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 at some point you have a single matter wave which characterizes the behavior of the system. And all the atoms feel this matter wave and behave in a coherent and extraordinary way. And this is the phenomenon of Bose-Einstein condensation. The realization of Bose-Einstein condensation in atomic gases has been a long sought goal for decades before 95. And because practically all the systems existing in nature, when you lower the temperature, become crystals, and they lose their quantum features, which can reveal the phenomenon of Bose-Einstein condensations. So atomic gases are not available in equilibrium at very, very low temperature. And so this would rule out the possibility of studying our physics, but this is not true, because this, and this is the crucial concept that it's important to realize, that atomic gases are available in conditions of metastable equilibrium, can live enough time in a gas phase before crystallizing. And so experimentalists are making the diluteness of the gases as big as possible in order to make this time of for the atoms to survive in the atomic phase for longer times. The theory to describe these atoms was formulated by Gross and Pytajewski. This is very, very, very old times, and this equation was derived to describe the properties of quantized vortex lines, which are the important manifestation of superfluidity. And what's important to know about the Gross-Pytajewski equation, that this is not the Schrödinger equation for many-body physics. And by the way, I understood that there was a debate between Pytajewski and Landau about this point, because Landau said, but your equation is interesting, but it violates nonlinearity of Schrödinger equation, because Schrödinger equation is a linear equation. This is a crucial point of quantum mechanics. But the main point is that this equation is nonlinear because it's not an equation for the many-body wave function, but it's an equation for the order parameter, which is a particular relevant parameter, a function, characterizing the physics of these systems. And in this nonlinearity, which is at the origin of many, many interesting phenomena like vortices, solitons, and many things we will discuss later, is the consequence of interaction effects. I would like to mention here Lev Pytajewski, because he passed away at the end of the month of August. And I would like to mention, I have collected, as I explained to Fernando, a series of memories written by French scientists. I would like to mention here this one that was written by Bill Phillips, his Nobel Prize for Physics. He said that Lev prepared our community for how to think about quantum degenerate gases before we even existed as a cold atomic gas community. So, because this paper by Lev was 61, and so much earlier than the field of atomic gases. So the question that we would like to address now is how we can realize such low temperatures and reach Bose-Einstein condensation. This is the first important question from the experimental point of view. And I would like to, I don't want to enter the details, also because I'm not an experimentalist, but I would like to mention the main points here. So first, you want to trap atoms, to keep them far from the walls, because otherwise hitting the walls, they would be heated by the walls, and so this we don't want. We want to keep separate from the walls. And so for this, you use magnetic or optical fields, but then you need ultra vacuum conditions in order to avoid that impurities in the cell, which are classical impurities of high temperature, will kill by colliding the cold atoms. And then we need very dilute gases, as I said before, to avoid the crystallization. And this is a very, very crucial requirement because you cannot realize Bose-Einstein condensation with a gas with the density of air, for example. It's impossible at least for the moment. We don't know, of course, in general. And then, because since the system is very dilute, the distance between atoms is very large, and if you want to obtain quantum regimes, you have to work at very, very low temperature, so that the thermal wavelength should be larger than this interatomic distance. All these points call for a great technological challenges of modern atomic physics. People started working along this direction at the end of the 70s, in the 80s, but only in the 90s were able to reach the goal of obtaining Bose-Einstein condensation. I would like to show here an experimental device used to realize the Bose-Einstein condensation. This is in the lab of Eric Cornell, who first realized the Bose-Einstein condensation in Colorado. And you can see here the cell. This is a glass cell. The size of the cell is like this, 20, 30 centimeter. And you have the magnetic, the coils generating magnetic fields which are confine the atoms, which are inside this cell, which should be empty, should be ultra vacuum cell without impurities of other atoms. And then you need lasers to make experiment, both to produce the beams of atoms entering the cell, but also for measuring the properties of these systems. And finally, in '95, thanks to this advanced technology, it was possible to realize Bose-Einstein condensation. And you see that by lowering the temperature, you reach a situation where all the atoms occupy a single state, which is the state inside the enharmonic trap. And this is provided by this strong peak here. And this is the phenomenon of Bose-Einstein condensation, which can be summarized with this sentence. Below a certain temperature, a macroscopic fraction of the whole system occupies the same single particle states. And this is the very peculiar phenomena which emphasizes the bosonic nature of the system. This cannot be obtained for fermions, because fermions do not like to stay in the same single particle state, but can be obtained also for fermions if you produce pairs of fermions. But I will not discuss too much this point now. In '97, the Nobel Prize was given to the people who realized these new techniques of trapping and cooling, but these were not the authors of Bose-Einstein condensation. And so, by the way, in '97, which is 2 years after Bose-Einstein condensation, many of us were surprised why the Nobel Committee did not give the Nobel Prize to the people who realized Bose-Einstein condensation. But the committee was careful. They decided that these people deserved the first Nobel Prize because they created a condition for reaching Bose-Einstein condensation. And only 4 years later, Eric Cornell, Wolfgang Kettel, Carl Weimann got the Nobel Prize for the achievement of Bose-Einstein condensation. After the first realization of Bose-Einstein condensation, the experimental and theoretical activity in the field has become a well-established field of research. And a fundamental interest for the investigation of quantum phenomena, and involves thousands of researchers around the world. I don't know how many labs are able now to produce Bose-Einstein condensation or ultra-cold gases, but probably there will be 100 typically. But there are more than 3,000-4,000 researchers working both for experimentally and theoretically on this subject. And now let's go to see what are the new important features which make this field of physics so interesting and attractive. And I would like here to present a very personal and incomplete overview of the most important achievements in the field, and it's impossible to cite all the important experiments, and this, of course, this selection follows of my interest in particular, and it's personal, and this I would like to emphasize this point. But what is certainly important in general, that all these experimental achievements, or practically almost all, have been stimulated by important theoretical works. And this confirms the crucial collaboration between theoretical and experimental research in this rapidly evolving field of physics. And I might say this is what I like the more when I enter in this field. Because, for example, I was personally coming from nuclear physics at the beginning. But in nuclear physics, the relationship between theorists and experimentalists is not so easy, because first, for doing experiment, you need very large, big labs. So you cannot work day by day in the same place. And so the time scale for developing the research activities is very different in experiments and in theory. While in our field, we can run collaborations with the theorists with experimentalists and vice versa in a very, very friendly way and very easy way. And this is, this at least was my experience, and for this I am very happy to have been involved in this type of physics. So let me start with this fast review, but what is the time? First step, okay, very good. So this I already said. In 95, in Gila and at MIT, they were able to realize Bose-Einstein condensation, in particular to observe that a microscopic number of atoms, so a finite fraction of atoms occupying the single particle states, n0, with respect to the total number of atoms, are staying in this state. This experiment was followed by very crucial experiments. And the day after, in particular, this experiment done at MIT, at the Kettle labs, it was possible to see that these atoms can interfere, so they behave like waves. So it's not obvious that atoms can behave like waves, and they can interfere and they give rise to interference fringes. And this was the proof that coherence and the interference phenomena plays a crucial role in this field of physics. In the same year, again in MIT, Kettle was able to prove that this Bose-Einstein condensed gases are able to oscillate following the hydrodynamic theory of superfluids. And just to give a flavor of what the collaboration between theories and experimental means, since I have worked a lot on these things, I cite a very interesting example. In the beginning of '96, there was the first meeting on Bose-Einstein condensation after the experimental discovery, and this was in Les Houches. And at that time, I gave a talk on the collective oscillations, because stimulated by the first experiment derived the equation of hydrodynamics. And at the end of the talk, both Cornell and Kettle contacted me saying, but this is a very easy experiment. We can do in 1 or 2 weeks. They went back at the conference and they realized the experiment. And by the way, they published the paper before me because I had problem with the referees. This is an interesting story. Just to show how important is the interaction between theorists and experimentalists. 1999, a crucial experiment was done again by Kettle, who arrived the first in producing BC, second in producing BC, but then because of the important achievement that he obtained immediately after, He deserved also the Nobel Prize together with David Cornell. So this is a very important experiment where it was shown that by applying a magnetic field, a proper magnetic field to the atoms, you can change the value of the scattering length, of the interaction between atoms. So it's possible to manipulate the interaction among atoms in a very simple way by just adding a magnetic field. And this has opened an infinite amount of applications in the field, because this is the first case where a physical system, you can manipulate by hand the interaction between atoms, and they can become even negative, because you see that the scattering length is positive here, becomes negative on the other side. And this had a tremendous impact, for example, in the case of Fermi gases, where it's possible to produce superfluidity, as I will show soon. 2000 is the year of quantized vortices, and the fundamental contribution was given by the Jean Delebarre group in Paris. And this, by the way, this is the most beautiful experiment proving the correctness of Gross-Pitayevsky equation, because Gross-Pitayevsky equation was Pitayevsky derived this equation to describe the structure of quantized vortices. Then in 2000, in a group of Oxford, they were able to measure the moment of inertia of these gases, revealing a phenomenon of superfluidity. And by the way, also in this case, we provided a theoretical. This is also an interesting story. We put on the archive our paper. In Oxford, experimentally saw the paper, and immediately did the experiment and confirmed the predicted reduction of the moment of inertia with respect to the classical solid behavior, revealing the effects of superfluidity. 2001 is a crucial year. Many of these years are crucial, but this, I would say, is one of the most important in the field, because they were able, by applying optical potential, so lasers generating strong localization of atoms and separated from a well to another, they were able to reveal the existence of the superfluid insulator transitions. And this opened really a new era in the field, where you can study phenomena of solid-state physics, and with all the models like Bose-Hubbard and Fermi-Hubbard models, so this experiment was really opening a new era in our field. 2003 is the year of fermions. At least three groups simultaneously in 2003 published the first evidence of Bose-Einstein condensation of molecules emerging from a Fermi sea. Here, the first and most important contribution was done by Debbie Jean at Gila, who sadly passed away because of illness. And here you see that by using the Feshbach resonance, where you can change the value of the scattering length, you can produce conditions for revealing in a very clear way this formation of pairs of fermions, and pairs of fermions are bosons. And this is an interesting prediction of quantum statistical mechanics. 2004 is another important direction for research concerning the Josephson oscillations. We had some discussion before, and the group of Heidelberg by Marcus Oberthaler, they were able to generate atoms confined in two wells, and then you can generate an oscillation of the atoms can cross the barrier via tunneling phenomena and oscillate, giving rise to a Josephson oscillation. And in addition, if the imbalance is too large, we have also another important phenomenon, which is self-trapping. And this is also a very beautiful piece of a story of a novel field. In 2004, this is a collaboration that I had with Eric Cornell in 2004. The idea was to use atoms, Bose-Einstein condensed gases, to reveal phenomena predicted in quantum electromagnetic conditions, where you have the fluctuations of the electromagnetic field, quantum and thermal, can give rise to a new type of forces, which are known as Casimir-Porter forces, where Pytajewski had been working for a while when he was in Russia with the Dialashinsky. After? Okay, very good. And we were able to observe that these thermal and quantum fluctuations give rise to different potential near the substrate of semiconductor. And you can measure this force by studying the effects on the collective oscillations. And this was the first measurement of the temperature dependence of the Casimir-Porter force. 2005, the MIT team was able to measure quantized vortices not only in the Bose gas, as we had shown before, but also in the Fermi superfluids. And this is much more challenging because you have to play again with these flashback resonances of which provide a tuning of the scattering length. And this, by the way, opened a way to the study of superfluidity in the Fermi superfluids case. 2007, this is just connected with this. MIT, they were able to observe the absence of viscosity in the unitary Fermi superfluid. But so by increasing the velocity of an impurity, you can see that if the velocity is more than the subcritical value, nothing happens. If the velocity increases, you have a heating effect that is revealed experimentally in this diagram. Experiments of this type had been done also for bosons, but the Fermi unitary gas is much more strongly interacting and is more suitable to study superfluid phenomena than the case of bosons. 2008, this is also another interesting direction of interplay between cold gases and solid state and statistical physics. We have the experiment on the Anderson localization, where by adding some impurities to the system, it's possible to observe that the system is, instead of expanding like this in the absence of impurities, of disorder, remains localized according to Anderson theory. And this was possible because interactions in these conditions, interaction between atoms is very, very small. And so practically you have a competition between the single particle behavior and the effect of disorder. And this was, thanks to the flashback resonance, it was possible to tune the scattering length particle equal to 0 and to reveal these features. Then 2008 is also an important year because the activity on the dipolar interaction started with the important results, as I will show later. And the dipolar gases are interesting because differently from the other atoms that have been used before, interact with long-range interactions because of their strong magnetic moments. And the interaction is long-range and also anisotropic. And this gives rise to a new many-body series of phenomena that I have not the time here to discuss. But just to mention that now we have the possibility to work with long-range interactions, and this is something that before was not possible. 2009, in the group, mainly in the group of Markus Greiner, an impressive improvement in the selectivity of and the control of single atoms and the arrays of atoms was possible. And starting from this year, essentially, it has been possible to have a control, a microscopic control of single atoms. And this is a very important possibility also in view of quantum information, quantum control approaches, which are now very, very popular. So this is also the beginning of a new era of experiments and theoretical work, by the way. Then in 2009, the same year, it was also possible to realize, to create artificial magnetic fields. Artificial magnetic fields using proper laser techniques. And in this way, it's possible to generate vortices, creating some new gauge fields in the Hamiltonian. And you can generate vortices with using the spin orbit coupled gases. And this is also the beginning of a new adventure where I am personally involved. 2012, the activity on the superfluid, Fermi superfluid gases became more advanced. In particular, it was possible to measure thermodynamics. And some of you are probably familiar with the lambda transition in superfluid helium. And here, the similar feature is exhibited by the Fermi superfluid gas. You have this lambda type of transition. For temperatures larger than this value, the system is normal. For temperatures smaller, becomes superfluid. Of course, a lot of theoretical works. Concerning all the things that I said, there are many, many theoretical works, and I had not the time, and it was not in the spirit of the colloquium to show the theoretical methods, because these are too complex to be summarized in 1 hour seminar. 2012, another important direction is concerned the role of low dimensionality. So thanks to optical lattices, it's possible to produce low-dimensional systems, two-dimensional or one-dimensional systems. In particular, in 2 dimensions, there are new phase transitions that are characterizing the system, the Berezinski-Kosterlitz-Thouless transition, and this was observed for the first time in the group of Jean de Liban at École Normale. The year after, this is also a collaboration where we have been involved in Trento. In Innsbruck, they were able to measure the propagation of second sound, which is one of the key predictions of Landau theory of superfluids at final temperature. And starting from this experiment, it's possible also to extract and the temperature dependence of the superfluid fraction that you have as a function of temperature. And this is especially important, in my opinion, because in helium, this experiment was possible only for the Bose case, while here was done for the Fermi superfluids. And so this was the first, in general, first measurement of second sound and the superfluid density in a Fermi superfluid. 2013, our experimental team in Trento were able to generate with the Kibble-Zucker mechanism, which corresponds to a fast ramping of the temperature through the transition to generate quantum defects. And this was, we were very proud. I was not involved in this paper, but this experimental paper done in Trento that gained also the cover of Nature Physics. 2014, another important direction which makes links with the community of solid-state physics. In Eslinger, in Zurich, they were able to measure the conductance in atomic Fermi gases and the typical plateau predicted by the theory when you change the gate potentials, forming these currents from between two sides of the system. This is another important and interesting experiment to mention. This was done in Israel, in Haifa, and was the observation of phenomena directly related to the Hawking radiation. So this opens a new direction. By the way, Fernando is also involved in some collaboration on these topics. It's possible to simulate what in high-energy physics and gravitational physics is known as the physics of black holes, by studying the radiation produced by quantum fluctuation phenomena. This is also a very active field of research, and as I try to show in this my presentation, there are many important experiments which opened a new direction, new fields, enlarging the community involved in these activities. Like, for example, the direction of increasing in a synthetic way, in artificial way, the dimensions of the system. Now it's possible to create a system with 4 dimensions by playing with the spin degree of freedom. And this is also a very active field of research. And then I am always saying this is very important, all are important, but this I think is also very important, is the creation of self-bound droplets in dipolar gases. Because of, as I said, in dipolar gases you have a long range and anisotropic behavior in the two-body interactions. Because of this, it's possible to generate some condition where you form self-bound droplets, which are kind of liquid clusters. And this was done, the first experiment was done by Tilman Pfau in Stuttgart. But the year after, another important direction, which again by Marcus Greiner, was the realization of the first example of a Fermi-Hubbard antiferromagnet. This is a basic and fundamental model for many-body physics at low temperature, where you have the frustration efforts entering in the solution of the many-body system. And with cold atoms, now it's possible to simulate this system. This is a typical example of quantum simulation. So use of atoms to simulate phenomena which are expected to be relevant in other fields of science. 2017, the group of Ketterle measured for the first time interference with Bragg scattering, interference revealing the structure of stripe phase in the, so essentially the phenomenon of supersolidity. Supersolidity is a phenomenon where you have simultaneously the behavior of superfluid and the behavior of a crystal, and which looks a little bit paradox. But now it's possible to realize this configuration with supersolids. And at the same time, more or less, in Barcelona, the group of Letizia Teruel, they obtained quantum droplets in Bose-Einstein conduction mixtures. So the first quantum droplets were done with the dipolar gases by Pfau 2 years before. But in Barcelona, they were able to do the formation using mixtures of two bosonic gases. And then here we have, we are approaching the end. We are going closer to the end. The 2019 was the year of supersolidity. The first important experiment, which was not yet supersolidity, was the group by Francesca Ferlaino in Innsbruck. They were able to, by tuning the interaction, it's possible to generate a Roton minimum in the excitation spectrum. And when this Roton minimum becomes too close to zero, the gap close to zero, we have a collapse. In the experiment that was done in 2018, but published in 2099, they didn't realize the supersolid, but the mechanism for generating the supersolid. And this was observed, again, the same year by the group of Pisa, Stuttgart, and Innsbruck, where you can observe a spontaneous breaking of translational invariance in the system, the formation of big clusters, as revealed by this beautiful image. And here, the same year, this we are also involved in Trento. We understood the physics of this system, because they give, when you have a supersolid, you have a new class of collective excitations, or gapless collective oscillations, they are called Goldstone modes. And we have explored the nature of these Goldstone modes, and we have measured them. So they have measured in Pisa, but in tight collaboration with us. And in Trento, we investigated the behavior of the moment of inertia. And I would like to conclude my presentation with this beautiful image. Again, Francesco Ferlaino in Innsbruck. They were able to generate for the first time a two-dimensional supersolid. And you have here a cluster of a system of 7 clusters, big clusters, each containing thousands of atoms, and they are formed spontaneously because of the proper balance between the dipolar and the contact interactions. And this is, now we are waiting for new experiment concerning the presence of quantum vortices in this system, and many other things. This was not the last slide, because 2021, we had a very beautiful experiment in a group of Azibabic in Cambridge, revealing the jump in the superfluid density at the Berezinski constant-Staulis transition. And this was, for the first time, was observed in so nice way in these cold cases set up. Okay, what are the conclusions? The conclusion is that after the first realization of BEC in 1995, this field has become a very active field of research of fundamental interest, because we are touching in this activity many fundamental issues, but also hopefully some applicative possibilities for other, let's say, purposes. But in general, all these phenomena are related to the behavior of quantum physics, which is the real reference theoretical framework for us. I would like to mention some perspectives in the field. The field of synthetic dimension is very promising, and the use of synthetic gauge fields in both Bose and Fermi gases, the possibility of introducing non-abelian gauge fields, which will open important connection with the relevant problems in high energy physics, the development of the simulation of lattice gauge theories, the new topological properties of quantum method that can be now, this is very, very important field. I know that there is a review paper written by many authors, theorists and experimentalists, and also from Trento, Jacopo Carusotti is one of the authors. This paper in 2 years has obtained already 2,000 citations, just to give an idea of the impact of this field of research. And then the problem of entanglement and many-body localization, and in general of quantum simulation of many different phenomena with ultra-cold atomic gases. The quantum computer is one of the aims, of course, in this connection, but we don't know what we can predict, because predicting the development in this field of research is impossible. And at the beginning, many people said, but what do you do with these atoms? They are so simple and trivial that there is no interest in physics after the first experiment. Especially people from condensed matter physics were raising this doubt about the possibility for the future developments. And now I think that all agree that this field is really rich and interesting. I would like to show a photograph of the Trento team with whom we have many collaborations from the theory side, but also experimentally. And this, by the way, is the last photograph of Lev Pitaevsky in our group, because after this, there was the pandemic, and then he became ill, and we had no other opportunities to make a photo together with him. Thank you very much.
Sí. Okay. Thank you very much, Sandro, for this very nice and illuminating talk. There is time for a few questions. One question, José Luis. Yeah.
Yes, thank you. Could you please tell us a few words about how to reach and to measure such low temperatures?
Sorry, I didn't.
Yes, can you tell us, please, a few words about how to measure and how to reach such low temperatures as we need for the Bose-Einstein condensation?
I'm sorry, but
how to reach and how to measure
how to measure Bose-Einstein, how do we measure
the temperature of the system?
Okay. So I can say, for example, if you want to measure the temperature, the clever way for this system is to study, to measure the density profiles on the tails. Because when you are in the tails of these systems, this is a big advantage of having harmonic trapping, for example, for these systems. When you go far from the center, the system becomes very dilute because the density decreases when you go far from the center, and the system becomes classical. So in the tails, the system is classical, and so you can describe the density profile using Boltzmann distribution of the form E minus V x squared, which is the harmonic potential, divided kT. And since we know exactly the form of the potential, you can measure the density, you can measure the temperature.
Okay. More questions? I have one question. Could you go to the transparency of Hawking radiation? Can you go back? Well, meanwhile, I would like to say that the nice summary that Sandro Stringari has made of the field, he has made very important contributions in most of the things that he mentioned. Also, I think you can have an idea of how rich the field is. It can be simulated essentially of almost everything in physics. I wanted to emphasize that in this Hawking radiation paper, Juan Ramón Muñoz de Nova, who is a Marie Curie fellow here in the Facultad, was the first author of that Nature paper, and officially he contributed crucially both to the theory and the experiment. So it's something to remark.
I didn't know.
No, but I wanted.
Okay,
I would like people to know that. Some people know
yes.
that. Okay, and apart from that, I would like to ask one question. Now it is possible to have relative. So historically, the first trapped gases, quantum gases, have been harmonically trapped. And now, since a few years ago, it is possible to trap them in boxes, which are like cubic boxes. There are some groups that do important work on that. I think, could you comment on the possibilities that it offers?
Yeah, of course. The harmonic trap has many advantages because you can control exactly from a theoretical point of view what happens in the system. In the box, you should treat the potential, and this is not completely obvious in some sense. But the advantage of the box trap is that you can reach what is usually understood as the thermodynamic limit when you have a uniform systems. And I would like to mention an important achievement in this direction is the last one that I mentioned, this one. This experiment where the Bose-Einstein transition was observed and understood was possible because the system was a box. It's a two-dimensional box, and Ati Babic and Cambridge, together with Dalibor, are the people who have introduced these two-dimensional boxes. And so many important physical properties can be understood better, and probably new things that was not possible to measure in the harmonic trap. Now they will be measured in the box. So this belongs to the future. And by the way, accidentally, this was the last slide I presented in my presentation.
Very well, thank you. Is there any more questions? Well, Sandro will be here during the day, for the rest of the day, and tomorrow he's participating in a workshop that will take place here, I think in this room, I'm not sure, but anyway, one of these Aula Magnas. Okay, so then maybe we can close the meeting, and we thank again Sandro for this very nice